The National Electrical Code, or NEC, provides guidelines for electrical installations, including determining the number of circuits that can be supported by a particular service size. In the specific case of a 100 amp service, the NEC states that you can support a maximum of 20 circuits rated at 20 amps each. This seemingly contradictory situation, where 20 circuits at 20 amps each would theoretically draw 400 amps, far exceeding the 100 amp service capacity, is reconciled by the application of the 80% rule and the understanding that not all circuits will be fully loaded simultaneously. The 80% rule is a fundamental concept in electrical design, and it is described in Article 210.19a(1) of the NEC. It dictates that a circuit breaker or overcurrent protection device should not be loaded to more than 80% of its rated capacity under continuous use. Continuous use is defined as a load operating for 3 hours or more. In simpler terms, an 100 amp breaker should ideally not supply more than 80 amps of continuous load. This safety margin is crucial for preventing overheating of conductors and breakers, minimizing the risk of fire, and ensuring the longevity and reliability of the electrical system. Applying the 80% rule to the 100 amp service, the maximum continuous load should not exceed 80 amps. This does not mean that only 80 amps worth of devices can be connected to the service. Instead, it means that the total load operating continuously for 3 hours or more should be kept at or below 80 amps. The apparent discrepancy between the potential 400 amps from 20 circuits at 20 amps each and the 100 amp service rating, or the 80 amp continuous load limit, is resolved by several factors. Firstly, diversity. Not all circuits are likely to be fully loaded simultaneously. Many circuits, power lighting, receptacles, or small appliances that draw current intermittently and far below their maximum rated capacity. Secondly, load calculations. The NEC mandates that electrical systems be designed based on calculated loads rather than simply adding up the maximum ratings of all connected devices. These calculations take into account demand factors, which are statistical estimations of how much of the total connected load is likely to be in use at any given time. Thirdly, non-continuous loads. Most residential and commercial loads are not continuous. Lights are switched off, appliances cycle on and off, and receptacles are not constantly loaded to their maximum capacity. Consequently, the average load on each circuit is typically far less than its 20 amp rating. To determine the actual number of 20 amp circuits that can be safely installed on a 100 amp service, a thorough load calculation must be performed. This involves, firstly, identifying all loads, list all appliances, lighting fixtures, receptacles, and other electrical devices that will be connected to the service. Secondly, determining the amperage of each load. Find the current draw in amps for each device, either from its nameplate or by dividing its wattage by the voltage, typically 120 volts for small appliances and lighting, or 240 volts for large appliances like stoves and dryers. Thirdly, applying demand factors. Use the demand factors provided in the NEC to estimate the actual load that each circuit will draw. These factors account for the fact that not all devices will be operating simultaneously. Fourthly, calculating the total load. Sum up the adjusted amperage for all loads to determine the total calculated load on the service. Fifthly, comparing to service capacity. Ensure that the total calculated load does not exceed 80% of the 100 amp service rating, which is 80 amps. If the total calculated load exceeds 80 amps, reduce the number of circuits or redistribute the loads to stay within a limit. For example, consider a scenario where a 100 amp service is supplying power to a small apartment. The apartment has the following loads. Firstly, general lighting and receptacles, assumed to be 10-20 amp circuits, each with an estimated demand factor of 50%, resulting in a load of 10 amps per circuit. Secondly, a refrigerator, a dedicated 20 amp circuit with a demand factor of 100%, drawing 8 amps continuously. Thirdly, an electric stove, a dedicated 50 amp circuit with a demand factor of 40%, drawing 20 amps. Fourthly, an electric water heater, a dedicated 30 amp circuit with a demand factor of 100%, drawing 12.5 amps. Fifthly, an air conditioner, a dedicated 20 amp circuit with a demand factor of 75%, drawing 15 amps. Calculating the total load. Firstly, lighting and receptacles, 10 circuits multiplied by 10 amps per circuit equals 100 amps. Secondly, refrigerator, 8 amps. Thirdly, electric stove, 20 amps. Fourthly, electric water heater, 12.5 amps. Fifthly, air conditioner, 15 amps. The total calculated load is 100 amps plus 8 amps plus 20 amps plus 12.5 amps plus 15 amps, which equals 155.5 amps. However, the demand factor for the lighting and receptacles is 50%, so the adjusted load is 100 amps multiplied by 0.5, which equals 50 amps. Therefore, the total adjusted load is 50 amps plus 8 amps plus 20 amps plus 12.5 amps plus 15 amps, which equals 105.5 amps. In this case, the total calculated load exceeds the 80 amp limit, so some adjustments would be necessary. This might involve reducing the number of general lighting and receptacle circuits, using energy-efficient appliances to lower the overall load, or upgrading the service to a higher amperage. While the NEC allows for a theoretical maximum of 20 circuits at 20 amps each on a 100 amp service, the actual number that can be safely installed depends on a careful load calculation that takes into account demand factors and the 80% rule. It is crucial to consult with a qualified electrician to perform these calculations and ensure that the electrical system is safe and compliant with the NEC. Simply installing the maximum number of circuits without considering the actual loads can lead to overloaded circuits, tripped breakers, and potentially hazardous situations. Furthermore, local electrical codes and regulations may have additional requirements or restrictions that must be followed. These codes may vary depending on the jurisdiction and may be more stringent than the NEC in some areas. Therefore, it is essential to be aware of and comply with all applicable codes and regulations. In addition to the 80% rule and load calculations, there are other important considerations when designing and installing electrical circuits. Firstly, conductor sizing. The size of the wires used to carry electricity must be appropriate for the amperage of the circuit. The NEC provides tables that specify the minimum wire size for various amperage ratings. Using undersized wires can lead to overheating and fire hazards. Secondly, overcurrent protection. Each circuit must be protected by a circuit breaker or fuse of the appropriate size. The overcurrent protection device is designed to trip or blow if the circuit is overloaded, preventing damage to the wiring and appliances. Thirdly, grounding. Proper grounding is essential for safety. Grounding provides a path for fault current to flow back to the source, causing the circuit breaker to trip and preventing electrical shock. Fourthly, GFCI protection. Ground fault circuit interrupters, or GFCIs, are required in areas where there is a risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. GFCIs detect even small amounts of current leakage and quickly shut off the power, preventing serious injury. Fifthly, arc fault circuit interrupters, or RSIs, are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. RSIs are required in many areas of the home, such as bedrooms and living rooms. In conclusion, determining the number of 20 amp circuits that can be safely installed on a 100 amp service is not a simple matter of dividing the service amperage by the circuit amperage. It requires a thorough understanding of the NEC, load calculations, demand factors, and the 80% rule. It is always best to consult with a qualified electrician to ensure that the electrical system is safe, compliant with all applicable codes and regulations, and meets the specific needs of the application. Ignoring these factors can lead to dangerous and costly consequences. The NEC is a comprehensive set of standards that covers all aspects of electrical installations. It is updated every 3 years to reflect changes in technology and best practices. The NEC is not law, but it is widely adopted by states and local jurisdictions as the basis for their electrical codes. Familiarity with the NEC is essential for anyone involved in electrical work, from electricians and contractors to homeowners and building owners. Understanding the principles behind the NEC helps to ensure that electrical systems are designed and installed safely and reliably. The NEC provides detailed guidelines on a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It also includes specific requirements for different types of occupancies, such as residential, commercial, and industrial buildings. The NEC is a valuable resource for anyone who wants to learn more about electrical safety and best practices. There are many resources available to help people learn about the NEC, including training courses, online forums, and publications from the National Fire Protection Association, or NFPA, which publishes the NEC. Investing time and effort in learning about the NEC can help to prevent electrical hazards and ensure the safety of people and property. In addition to the NEC, there are other standards and regulations that may apply to electrical installations. These include standards from organizations such as the Underwriters Laboratories, or OL, and the Institute of Electrical and Electronics Engineers, or IEE. It is important to be aware of all applicable standards and regulations and to follow them carefully. Electrical work can be dangerous, and it is essential to take all necessary precautions to protect yourself and others. This includes wearing appropriate personal protective equipment such as gloves and safety glasses, and following safe work practices. Never work on electrical equipment that is energized unless you are qualified to do so and have taken all necessary safety precautions. If you are not comfortable working on electrical equipment, it is always best to hire a qualified electrician. A qualified electrician has the knowledge, skills, and experience to perform electrical work safely and correctly. They can also help you to ensure that your electrical system is compliant with all applicable codes and regulations. Choosing a qualified electrician is an important decision. Look for an electrician who is licensed, insured, and has a good reputation. Ask for references and check online reviews to get an idea of their quality of work. A good electrician will be able to answer your questions clearly and explain the work that needs to be done. They will also provide you with a written estimate before starting any work. In summary, understanding the principles behind electrical installations, following the NEC and other applicable standards and regulations, and hiring a qualified electrician are all essential for ensuring the safety and reliability of electrical systems. Taking these steps can help to prevent electrical hazards and protect people and property. Remember that electrical work is not a do-it-yourself project for most people. It requires specialized knowledge, skills, and equipment. Always seek professional help when dealing with electrical systems. The information provided here is for general educational purposes only and should not be considered as a substitute for professional advice. Always consult with a qualified electrician before making any decisions about your electrical system. Finally, remember that electrical safety is everyone's responsibility. By being aware of the potential hazards and taking the necessary precautions, you can help to create a safer environment for yourself, your family, and your community.